It could reach altitudes more than 15,000 meters or 50,000 feet and fly nearly 10,000 kilometers or around 6,000 miles, nearly a quarter of the Earth's circumference, without refueling. It can penetrate even the most heavily defended airspace, deliver up to 18,000 kilograms of bombs with pinpoint accuracy, and slip out again, all while remaining orbit invisible to radar. And it looks like nothing else flying today, with no fuselage or tail and an organic bat-like form that seems more like it was grown rather than built. It looks like something straight out of science fiction. It is, of course, the Northrop Grumman B-2 Spirit stealth bomber, one of the most advanced and exotic aircraft ever made. It's also by far the most expensive, with each of these state-of-the-art aircraft commanding an eye-watering price tag of over $2 billion. But what makes the B-2 so special? How can such a large craft be effectively invisible to enemy air defenses? What was this technological wonder originally designed for, and what makes it so extraordinarily pricey? Let's find out as we dive into the fascinating history of one of aerospace engineering's greatest and most controversial achievements. By far, the B-2's most distinctive attribute is its lack of a distinct fuselage, tail, and other features we normally expect to see on an aircraft. Indeed, it is one of the most successful implementations of the flying wing concept, long considered the holy grail of aerospace engineering. The flying wing is the aircraft distilled to its purest form, offering the least drag, the greatest structural efficiency, and the greatest performance for a given size and weight. But while it is only relatively recently that engineers managed to make this exotic space-age design a practical reality, the basic concept of a flying wing is actually far older than you might think, dating back to the very dawn of aviation. Even in the earliest days of heavy-than-air flight, inventors realized that the conventional fuselage wings tailplane architecture that would eventually become standard for most aircraft was not necessarily the most efficient. As early as 1904, just 1 year after the Wright brothers' historic flight, former British Army soldier Lieutenant John W. Dunne conceived of an innovative aircraft design that would be naturally stable in all three axes of control: roll, pitch, and yaw, making it much easier and safer for a pilot to fly. Dunne's design featured wings that were sharply swept rearward, much as they are on modern fighter jets, though in Dunne's case, this was done for stability reasons rather than to reduce drag at high speeds. Crucially, the wing's angle of incidence, that is, their angle relative to the aircraft's centerline, varied progressively along their length, starting out steeper at the roots and becoming progressively shallower out towards the wingtips. This arrangement, known today as a washout, along with the wing sweep placing the wingtips far behind the wing roots, made the aircraft inherently stable in pitch. For example, if the aircraft pitched upward, the wing roots, having a steeper angle of incidence than the wingtips, would stall or lose lift first. Meanwhile, the wingtips would still be producing lift, generating a torque that would pitch the aircraft back down to a level attitude. Conversely, if the aircraft pitched down, the wing roots would generate higher lift than the wingtips, creating a torque in the opposite direction that would pitch the aircraft back up. In addition, the wing wash ensured that airflow was preserved over the wingtips throughout a storm, maintaining the effectiveness of the ailerons, which control an aircraft in roll, and allowing the pilot to avoid a potentially lethal spin. In 1906, Dunne, who had developed heart disease during the Boer War and declared unfit for service, was assigned to the British Army's balloon factory at Farnborough, England, where he obtained official government funding to construct his radical new aircraft design. In 1907, he constructed a biplane glider dubbed the D-1, which, for reasons of secrecy, he flight tested at Blair Atoll, the estate of the Marquis of Tullibardine in the Scottish Highlands. Piloted by Colonel John E. Capper, commander of the balloon factory, D-1 made only a brief 8-second flight before crashing into a wall, damaging the aircraft and lightly injuring Capper. Nonetheless, the aircraft demonstrated the intended natural stability, and Dunne decided to immediately adapt it to powered flight. The rebuilt D-2 was fitted with propellers driven by a pair of 7.5 horsepower gasoline engines, but these proved underpowered and the aircraft failed to become airborne even when launched down an incline ramp. Several more versions followed, culminating in the D4, fitted with 25 horsepower engines and a 4-wheel fixed undercarriage. However, this aircraft also failed to make more than a few short hops, and in 1908, the Army pulled Dunne's funding. Undeterred, Dunne brought his design to aircraft manufacturer Short Brothers. Funded by the Blair Athol Aeroplane Syndicate, a company founded by the Marquis of Tullibardine in 1910, Short Brothers rolled out the Dunne D5. In addition to being swept and washed out, the D5's wings also featured a significant anhedral or downwards angle when viewed from the front. design meant to keep the aircraft stable in roll. In addition, the wingtips were capped with end panels, which not only increased stability in yaw, but also made the wings more efficient by reducing the formation of wingtip vortices. Having no conventional tail surfaces, the D-5 was controlled using special movable wingtip surfaces called elevons, which, as the name implies, combined the functions of elevators and ailerons. There was no rudder, yaw was controlled via the differential drag created by the elevons. Powered by a 60-horsepower engine, the D-5 made its maiden flight in the summer of 1910, witnessed by none other than Orville Wright. The flight was reported on in the June 18th issue of Flight magazine, with the editors noting, "One of the most important items recently chronicled in Flight was that recording the achievement of Lieutenant J.W. Dunne, who at Eastchurch in the Isle of Sheppey flew a distance of 2¼ miles on a machine of his own design, which displayed so much natural stability as to render the use of the control levers totally unnecessary, except so far as they were required for the purpose of directing the course." Indeed, Dunne reported being able to remove his hands from the controls in order to jot down notes. This marked the first successful flight of an inherently stable aeroplane. Earlier designs, especially those of the Wright brothers, were extremely unstable, requiring constant and often frantic control inputs from the pilot to keep them flying straight and level. It was also arguably the first flight of a flying wing, though purists argued that the D-5 was more of a tailless aircraft than a true flying wing, as it featured vertical stabilizer surfaces and the pilot's cabin was separate from and not integrated into the wing. Whatever the case, despite this historic achievement, the editors of Flight noted that, quote, "There is no doubt that this flight marks an important period in the development of the aeroplane, and although the outcome of it can only be vaguely surmised, this in no way detracts from its present importance and should increase rather than otherwise the amount of interest in the machine itself." Now, these words were to prove sadly prophetic. Dunne continued to develop ever more sophisticated versions of his design, culminating in the D-8. In 1913, a French pilot dramatically demonstrated the D-8's inherent stability by releasing the aircraft's controls and walking out onto the wing over a crowd of stunned onlookers. The design was soon licensed to French aircraft manufacturer Newport and American manufacturer Burgess, with small numbers of Burgess-Dunne biplanes being purchased by the US Army Signal Corps, the US Navy, and the Canadian Aviation Corps, the nation's first and short-lived air force. However, the outbreak of the First World War led to Dunne's research being abandoned in favor of more conventional aircraft designs. Meanwhile, military planners decided the Burgess-Dunne was ironically too stable, making it overly sluggish and unmaneuverable. As a result, none saw combat during the war. Meanwhile, aside from wing washout, few of Dunne's groundbreaking innovations were widely adopted. Had they been, the history of aircraft design might have been very different. But the quest for the flying wing, the platonic ideal of aircraft, persisted. The next major figure in the story of the flying wing was British test pilot and aeronautical engineer Geoffrey T.R. Hill. Like John Dunne, Hill was concerned about the inherent stability and safety of aircraft and sought to create a design that would be all but impossible to stall or spin. Using Dunne's designs as a starting point, in 1924, Hill, together with his wife, created a flying wing glider with a sharply swept, washed-out wing, which he dubbed the Pterodactyl. This prototype performed well, so Hill fitted it with a 35-horsepower engine and in 1925 demonstrated it before the British Secretary of State for Air, Sir Samuel Hoare. Impressed, Hoare directed the Air Ministry to fund a research program under the auspices of aircraft manufacturer Westland Aircraft, who took Hill on to direct the project. Over the next few years, Hill and Westland built and flew several increasingly sophisticated versions of the Pterodactyl, some of which were constructed to Air Ministry specifications and officially submitted for consideration as two-seater fighter aircraft for the Royal Air Force. However, as with the earlier Dunne designs, the Pterodactyls lost out to more conventional designs and the research project at Westland was finally abandoned in 1932. Meanwhile, in Germany, development of flying wings was attracting far more official enthusiasm. Early work on tailless and delta-wing aircraft was carried out by German aerodynamicist Alexander Lippisch, who in 1928 designed the world's first rocket-powered aircraft, the Lippisch Ant, or Duck. He would later go on to design the innovative but horrifically dangerous Messerschmitt Me-163 Comet rocket-powered interceptor, used in small numbers at the end of the Second World War, and for more on that please do check out our previous video, the German rocket fighter that dissolved its pilots alive. Lippisch's work on tailless aircraft was highly inspirational to Walter and Reimer Horten, two brothers from Göttingen who, like many young Germans during the interwar period, were obsessed with the sport of gliding. With Germany prohibited by the 1919 Treaty of Versailles from building an air force, gliding clubs provided an expedient and legal means of secretly training the nation's next generation of military pilots. Starting in 1931, the Horton brothers began building and flying their own glider designs. Inspired by the work of Lippisch, they quickly moved away from conventional designs towards radically sleek, tailless flying wings. To further reduce frontal area and thus drag, the pilot lay prone under a streamlined, closely faired canopy. While the Horton's first few designs were unsuccessful, the Horton H4, introduced in 1941, demonstrated exceptional performance, achieving a maximum speed of 200 km per hour. The timing of this development could not have been better, for in 1943, Hermann Göring, head of the Luftwaffe, put out a requirement for a so-called 3x1000 bomber, which could carry 1,000 kilograms of bombs over 1,000 kilometers while flying at 1,000 kilometers an hour. Only jet propulsion could achieve the speeds required, but at the time, these were extremely fuel-hungry, requiring an exceptionally efficient airframe to achieve the required range and bomb load. The Horton brothers believed that their flying wing design held the key and submitted an official proposal to the Reich Air Ministry, or RLM. Their proposal was the only one which came close to meeting the stated performance requirements, and with the enthusiastic support of Göring, the project was approved under the initial designation of H09. As the Horton brothers lacked their own large-scale manufacturing facilities, the project was assigned to aircraft manufacturer Gothiger Wagenfabrik, or simply Gotha. The RLM issued an order of 100 production aircraft under the designation GO-229, which were to be fitted with a pair of 30mm cannons in addition to bomb racks so that they could double as fighters. In addition to its radical tailless design, the GO-229 had a number of other advanced features, including a primitive ejection seat and a pressure suit to allow the pilot to fly at high altitudes. However, to conserve scarce strategic materials like aluminium, the aircraft was constructed largely out of wood, with only the central section being built of welded steel tubes. But while aerodynamically efficient, the aircraft suffered from significant stability problems, especially in yaw. Normally, the vertical tail on an aircraft provides passive lateral stability. Without one, the GO-229 was prone to entering uncontrolled side slips and even potentially fatal flat spins. The Hortons addressed this problem through the use of split ailerons, which opened both upwards and downwards, creating the differential drag that took the place of rudder action. Nonetheless, the GO-229 required considerably more active control input from the pilot and was restricted in the bank angles that it could achieve. The first V1 airframe was nearly complete by the time the aircraft's BMW 109003A1 turbojet engines finally arrived, but to the Hortons' dismay, they turned out to be larger than anticipated and would not fit inside the GO-229's wings. V1 was thus flight tested as a glider throughout 1944, while V2 was modified to accept the more powerful, but even bulkier, Junkers 109004B1 engines. By this time, Germany's worsening strategic situation had forced the RLM to reduce its initial order of 100 aircraft to just 7 prototypes and 20 production aircraft. The B-2 prototype made its maiden flight on February 2, 1945, with Luftwaffe test pilot Lieutenant Erwin Ziller at the controls. The aircraft handled well, and Ziller went on to perform another successful test flight a few days later, reaching a top speed of 950 km per hour. However, 45 minutes into the third test flight on February 18th, one of the aircraft's engines caught fire and seized. Ziller performed a series of dives in an attempt to restart the engine, but eventually lost control and crashed just outside the airfield. He died of his injuries shortly thereafter. Work continued on the GO-229, but in April 1945, American troops overran the Gotha factory before the aircraft could see combat. The most complete prototype, V3, was shipped first to England and then to the United States for evaluation, though it never flew again. The exotic Nazi flying wing is currently on display at the Stephen F. Udzvar Hazy Center, the National Air and Space Museum's annex in Chantilly, Virginia. It is often claimed that the GO-229's unique shape, wooden construction, and special fireproof paint, which contained powdered charcoal, rendered the aircraft nearly invisible to radar, making it history's first stealth fighter. This, however, is not the case. In 2008, as part of a documentary produced by the National Geographic Channel, American aircraft manufacturer Northrop Grumman built a full-sized wooden mock-up of the GO-229 and mounted it on its radar cross-section range in Dayon, California. These tests revealed that the aircraft's radar cross-section was only around 90% of that of the Messerschmitt Bf-109, Germany's primary wartime fighter. Indeed, while the GO-229's wooden wing panels and clean shape, free of vertical stabilizers and other large flat surfaces, would theoretically have returned weaker radar echoes, this was almost completely offset by internal structures like the steel tubing cockpit frame and the engines, which were extremely reflective. And while the Hortons claimed to have used graphite in the GO-229's paint, none was found in the surviving prototype, and in any case tests have revealed that on its own, graphite is a poor radar absorber. However, the basic idea of the flying wing shape being being naturally stealthy was theoretically sound and would later be implemented in a far more effective manner in the B-2 Spirit. But while the GO-229 was one of the most innovative designs of the Second World War, the Horton brothers had even grander plans, including the Horton 18, a gigantic jet-powered flying wing bomber with a 40-meter wingspan. Submitted as part of the Langstrecke Bomber, or America Bomber project, the H-18 was designed to cross the Atlantic Ocean and attack targets in North America like New York City. The Hortons also envisioned a civilian airliner version capable of carrying 60 passengers across the Atlantic in unprecedented style and comfort. However, the war ended before either aircraft could leave the drawing board. Like many Germans, after the war, Reimar Horton moved to Argentina, where he joined the state aviation and transportation conglomerate DIN-FIA and began designing an unusual tailless transport aircraft called the FM-1 AE-38. Though based on his and his brother's earlier design, the 38 was not a true flying wing, featuring a large central fuselage section with clamshell doors for loading and unloading cargo. Development of the aircraft was slowed by political instability, and when it finally made its first test flights in 1960, it proved unstable, underpowered, and prone to engine overheating. The project was finally cancelled in 1962. While the Germans had taken the flying wing concept far, it would fall to an American, one Jack Knudsen Northrop, to carry it over the finish line. Incredibly, despite being regarded as one of history's great aircraft designers, Jack Northrop had little formal education, later stating that, quote, "My grammar school and high school education, outside of the school of hard knocks, was the only education I ever had. I didn't go to college, I didn't have any correspondence courses or anything of this sort." Born in New Jersey in 1895, but raised in Santa Barbara, California, Northrop began his aviation career in 1916 as a draftsman at the Lougheed Aircraft Manufacturing Company, which would later change the spelling of its name to the more familiar Lockheed. After briefly being drafted into the US Army during the First World War, he returned to civilian life and joined the Douglas Aircraft Company. There he participated in the design of the Douglas World Cruiser, 3 of which completed the first aerial circumnavigation of the globe between April 6th and September 28th, 1924. Returning to Lockheed in 1927, he was heavily involved in the design of the innovative Vega, a favorite of several pioneering aviators, including Amelia Earhart and Wiley Post. And to learn more about these towering aviation figures, please do check out our previous video, the one-eyed barnstormer who invented the spacesuit. In 1929, Northrop left Lockheed to found his own company, the Avian Corporation, where he began to pursue his ultimate aviation dream, realizing a practical flying wing. His first attempt, the X-21-6H, was an incremental step, featuring a large, thick wing, but retaining a traditional twin-boom tail for added stability. More significantly, the aircraft abandoned the traditional doped canvas or wood construction of most contemporary aircraft for an Alcat aluminium skin, a taste of what was to come. Powered by a 90-horsepower engine driving a pusher propeller, the X-21-6H made its first unofficial short hops at Mines Field, California on July 30th, 1929, with test pilot Eddie Belonde at the controls. It was then transported to Morrock Dry Lake Bed in the Mojave Desert, today Edwards Air Force Base, for official testing, making its first official flight on September 26th. Many more test flights followed, with Northrop and his team integrating various design modifications, including better landing gear and rudder extensions for added stability. Initial results were promising, with the X-21-6H exhibiting performance 25% greater than conventional aircraft of similar size, weight, and engine power. Unfortunately, the Great Depression soon caught up to Northrop, and in 1930 he was forced to sell the Avian Corporation to United Aircraft and Transport. Undeterred, in 1932 Northrop founded another company, Northrop Corporation, with the backing of Douglas Aircraft. This company produced a number of highly successful all-metal monoplanes, including the Gamma and Delta, the former of which completed the first aerial crossing of Antarctica in 1935. By 1939, the original Northrop Corporation had been wholly absorbed into Douglas Aircraft, so Northrop founded an identically named company based in Hawthorne, California, where after nearly a decade he finally resumed research on flying wings. While Northrop initially tried pitching a flying wing medium bomber to the US Army Air Corps, this failed to attract much interest, so he instead constructed a subscale proof-of-concept demonstrator to study the dynamics of flying wing designs. Known as the N-1M, the aircraft had a wingspan of 25 meters and was powered by two 65-horsepower engines driving pusher propellers. To counter the lateral instability common to all flying wings, Northrop gave the N-1M drooping wingtips, the angle of which could be adjusted on the ground to test different configurations. Similarly, the outer wing panels could be adjusted to create different angles of sweep. Flight testing began in July 1940 at Muroc, with the N-1M making its first very brief test flight on the 3rd when test pilot Vance Breeze accidentally hit a bump during high-speed taxi tests, launching the craft into the air. During the short 30-meter flight, Breeze found the N-1M to be easily controllable. However, the original engines proved greatly underpowered, and Breeze struggled to fly the aircraft more than 3 meters off the lake bed. Only when more powerful 117 horsepower engines were installed could the aircraft properly get airborne. The N-1M made approximately 100 test flights before being retired, collecting a wealth of valuable data on flying wing design. Among other things, the test program revealed that the drooping wingtips were unnecessary, and the company's next flying wing, the N-9, was built with straight wings. Though Northrop had previously failed to attract government interest in his research, things were about to change. In April 1941, the US Army Air Corps put out a request for a bomber that could carry 10,000 pounds of bombs over a range of 10,000 miles. Northrop submitted a version of the N-1 design, which was officially approved in October as the XB-35. The Army Air Corps initially contracted Northrop to build one full-size mock-up and 2 flying prototypes, but in 1942 they cancelled a previous order for 402 Marine B-33 Super Marauder medium bombers and instead split the contract between Northrop's XB-35 and Consolidated Aircraft's XB-36 design. As Northrop's Hawthorne factory was relatively small, production of the XB-35 was assigned to the Glenn L. Martin Company of Santa Ana, California. News of this exotic addition to the American arsenal captured the American imagination, with the New York Times breathlessly reporting, "Perhaps the day is not far distant when flying wing types will dominate the entire field of military, commercial, and private flying." The XB-35 was to be absolutely enormous, with a wingspan of 52 meters, longer even than the Boeing B-29 Superfortress, which was then under development. Given the enormous challenge of building such a gargantuan aircraft, especially with a configuration as new and unproven as a flying wing, Northrop once again decided to build 4 subscale flying mock-ups, designated the N-9M. With wingspans of 18 meters, the N-9Ms were powered by a pair of 269 horsepower engines, giving them a top speed of 160 kilometers an hour and a service ceiling of 6,000 meters. Flight testing began in December 1942, though engine reliability issues cut many of the early flights short. Then, on May 19, 1943, the aircraft experienced sudden control reversal and spiraled to the ground. Test pilot Max Constant was pinned to his seat by the control column and was unable to bail out, dying instantly on impact. In response, Northrop added Horton-style split-drag ailerons to the remaining N-9Ms to improve their lateral stability as well as more reliable engines. The test program resumed in 1945 and ended in late 1946, with the 3 remaining aircraft making a combined total of over 200 flights. During this period, several guest pilots were invited to take the controls, with Captain Glenn Edwards saying of the N-9M, "The airplane flew surprisingly well, was more stable and handled far better than most would expect." As we shall soon see, he may have come to regret that statement. Meanwhile, work proceeded on the XB-35, with the full-scale non-flying mock-up being completed in 1943. Northrop also worked on a number of related side projects, including the much smaller MX-324, which on July 5, 1944, became the first US-built aircraft to fly under rocket power. This aircraft became the basis for the XP-79, a small fighter powered by a pair of Westinghouse 19B turbojet engines. Not a true flying wing, the aircraft had a pair of small vertical tail surfaces for lateral stability, with the pilot lying prone between the 2 engines, as in the contemporary German Horten designs. Though armed with 450 caliber machine guns, the XP-79's leading edge was built out of solid magnesium to allow it to cut through the wings of enemy bombers, hence its unofficial name, the Flying Ram. The XP-79 made its first and only flight on September 12, 1945 at Muroc, but 15 minutes into the flight, the aircraft suddenly became uncontrollable and spiraled to the ground. Test pilot Harry Crosby attempted to bail out, but was struck by the aircraft and killed. The project was cancelled shortly thereafter. Northrop had originally intended to deliver the XB-35 in 1943, but constant delays caused by production problems and technical issues meant the war had already ended by the time the first prototype was completed in 1946. Worse still, with the war winding down and the need for new bombers rapidly decreasing, in May 1944, the Air Corps decided to cancel the XB-35 production contract. However, they continued to fund the construction of the prototype for research purposes. The completed aircraft looked like something out of science fiction, with a gargantuan shimmering wing half the size of a football field. The beast was propelled by 4 3,000 horsepower Pratt & Whitney R4360 turbo-supercharged Wasp major engines, driving twin contra-rotating propellers mounted in pusher configuration, allowing it to carry a 33,000 kilogram bomb load. The pilot and co-pilot sat beneath a fighter-style canopy offset to the left of the centerline, while 7 other crew members occupied various stations inside the wing's cavernous center section. Among these was a central gunner seated in a transparent blister at the rear of the aircraft, who operated 4 2-ton turrets by remote control. 2 more manned 4-gun turrets completed the defensive armament. The alien-looking craft fired the imagination of an American public enthralled by post-war technology and was extensively profiled in aviation and technology magazines and other popular publications. The XB-35 made its maiden flight on June 25, 1946, a short and uneventful trip from the Northrop facility in Hawthorne to Muroc Dry Lake bed. Unfortunately, subsequent test flights revealed a host of technical issues, mainly with the complex contra-rotating propellers. Though highly efficient aerodynamically, they proved highly unreliable and prone to excessive vibration, forcing Jack Northrop to ground the aircraft after only 19 flights and install more conventional single propellers. However, this greatly increased the XB-35's takeoff roll and reduced its top speed and ceiling. The complex exhaust system for the engines also proved frustratingly temperamental. Yet, despite these problems, the aircraft showed great promise, with Air Force magazine claiming in July 1946 that, quote, compared to a conventional airplane of equal power, weight, and fuel load, the flying wing will 1. Carry 1/4 more useful load, 2. Travel 1/4 farther with an identical fuel load, 3. Travel approximately 20% faster with the same thrust or applied horsepower. But there was a slight problem. The XB-35 had been designed to carry conventional bombs, the payload being distributed between multiple smaller bomb bays. This, however, prevented the XB-35 from carrying the first generation of atomic bombs, quickly becoming the de facto weapon of modern warfare. Bafflingly, the Air Force forbade Northrop from modifying the XB-35 to carry the standard Mark III Fat Man atomic bomb, while simultaneously refusing to accept the aircraft unless it could carry that very weapon. They also declared the aircraft's conventional piston propulsion scheme obsolete in the face of the rapidly accelerating jet age. Yet they continue to fund the project out of sheer necessity, with proponents arguing that the XB-35 and rival XB-36 were the only aircraft available with the necessary range to strike the Soviet Union and would likely remain so for many years. In an attempt to modernize the XB-35 and make it more attractive to the Air Force, in 1947, Northrop converted 3 of the 14 pre-production prototypes to jet propulsion, installing no fewer than 8 Allison J-35 turbojet engines for a combined thrust of 144 kilonewtons. Small dorsal and ventral fins were also added for increased lateral stability, while the defensive gun turrets were deleted. The new aircraft, designated the YB-49, first flew on October 22, 1947, and immediately showed far more promise than its piston-powered predecessor, achieving a top speed of 837 km per hour. It later set an unofficial endurance record by flying continuously above 12,000 meters for 6.5 hours straight. At the same time, however, the added weight of the jet engines and the larger quantity of fuel needed to feed them significantly reduced the aircraft's ceiling, range, and payload, making it even less suited as a strategic nuclear bomber. It also suffered from worrying lateral instability problems, with test pilot Lieutenant Glenn Edwards describing the prototype as, quote, the darndest airplane I've ever tried to do anything with, quite uncontrollable at times. Hope to be more favorably impressed as time goes on. But that day would never come, for during a test flight on June 5, 1948, the YB-49 suddenly broke apart in midair, killing Edwards' co-pilot Major Daniel Forbes and 3 other crew members. The cause of the crash was never definitively determined. In commemoration of Edwards' dedication to the pursuit of experimental flight research, in December 1949, Muroc Air Force Base was renamed in his honor. In spite of this tragedy, flight testing pressed on, with the experimental reconnaissance version of the YB-49, the YRB-49A, first taking to the skies in May 1950. However, less than a year later, the entire project was abruptly cancelled in favor of the rival Convair B-36 Peacemaker. While the piston-powered B-36 was arguably even more obsolete than the XB-35 or YB-49, it had one decisive advantage. Its bomb bay was large enough to carry atomic bombs and the even larger first-generation thermonuclear weapons or hydrogen bombs. And for more on the development of this earth-shattering weapon, please do check out our previous video, Who Invented the Hydrogen Bomb. But even if the XB-35 or YB-49 had been successfully modified to carry nuclear weapons, the reality was that Northrop had pushed the flying wing design to the limit of available technology. While aerodynamically efficient, flying wings are inherently unstable, and without some kind of automatic stability enhancement will always be difficult and even dangerous for pilots to control. Furthermore, fitting all the required components of a conventional aircraft, cockpits, engines, landing gear, fuel tanks, payload, etc., requires the wing section to be extremely thick, creating considerable drag and severely limiting the aircraft's performance. Nonetheless, the XB-35 and YB-49 programs provided the Northrop Corporation with a wealth of vital information on flying wings, meaning that when the technology finally caught up to the design, they would be perfectly positioned to create one of the most extraordinary aircraft ever built. Now, at long last, we come to the actual subject of today's video, the B-2 Spirit. But to understand the unusual design of this aircraft, it is important to understand the persistent strategic problem which led to its creation: how to get an atomic bomb to the heart of the Soviet Union. The Convair B-36 Peacemaker, which beat out the XB-35 and the XB-49, became Strategic Air Command's, or SAC's, primary strategic bomber in 1948. But while the aircraft had an enormous 40,000-kilogram payload capacity and could fly over 6,000 kilometers without refueling, it flew at a relatively low speed and altitude and was highly vulnerable to Soviet interceptor aircraft. Had nuclear war ever been declared, the lumbering peacemakers would likely have been shot out of the sky before they ever reached their targets. Several attempts were made to improve the performance and survivability of the aircraft, for example, by adding additional jet engines and even a deployable parasite fighter, the McDonnell XF-85 Goblin, to chase off enemy interceptors. But the inescapable truth was that the B-36 belonged to an earlier era of military aviation. The aircraft was finally retired in 1959, replaced by the more advanced jet-powered Boeing B-47 Stratojet and B-52 Stratofortress. The latter, in particular, became an icon of the Cold War. Between 1961 and 1968, nuclear-armed B-52s were placed on continuous airborne alert as part of Operation Chrome Dome, flying round-the-clock missions near the Soviet Union's northern borders. This ensured that even if the Soviets launched a first strike and destroyed most of the United States' nuclear arsenal on the ground, at least a few B-52s would remain in the air at any given time, ready to dash across the Soviet border to deliver a retaliatory strike. But while much faster and higher flying than the B-36, the B-52 was far from invulnerable. Though the aircraft was originally designed to fly higher than existing interceptors, rapid advances in Soviet surface-to-air missile technology quickly closed the gap, as dramatically illustrated by the shooting down of a high-flying Lockheed U-2 spy plane flown by Francis Gary Powers on May 1, 1960. In response, the United States developed a number of air-launched standoff missiles like the Douglas GAM-87 Skybolt, North American AGM-28 Hound Dog, and Boeing AGM-69 SRAM to allow B-52s to attack targets within the Soviet Union while remaining safely out of range of the Soviet air defenses. However, these were only a stopgap solution. To accurately strike targets deep within Soviet territory, a more radical type of bomber aircraft was needed, one that could fly far higher and faster than any interceptor or missile. This requirement led to the development of two highly advanced aircraft, the Convair B-58 Hustler, introduced in 1960, and the North American XB-70 Valkyrie, which was first flown in 1964. The former could reach a top speed of Mach 2 at an altitude of 19,000 meters, and the latter more than Mach 3 at 21,000 meters, nearly as fast as the Lockheed SR-71 Blackbird, the fastest active military aircraft in history. Yet despite this blistering performance, even the B-58 and XB-70 soon became vulnerable to the new generation of Soviet surface-to-air missiles, and the US Air Force was forced to switch tactics. Instead of flying high and fast, bombers would now be extremely low, hugging the ground and using the terrain to confuse enemy radar. Unfortunately, neither the B-58 nor the XB-70, which had been specifically designed for high-altitude flight, performed particularly well at low altitudes, leading to the former being retired in 1970 and the latter being cancelled in 1961 without ever entering service. The XB-70 continued to fly as a high-speed test platform until finally being retired in 1970. With the loss of the B-58 and XB-70, Strategic Air Command was left with only one operational strategic bomber, the B-52 Stratofortress, which despite its age remained in service thanks to its extreme adaptability and reliability. However, the B-52 was not well suited to the low-level penetrator/interdictor role, so the Air Force set about developing more purpose-built aircraft. The first of these was the General Dynamics F-111 Aardvark, which could carry out tactical, low-level strikes but lacked the intercontinental range needed for strategic nuclear bombing. That role would instead be filled by the Rockwell International B-1 Lancer, which was designed to combine the Mach 2 capability of the B-58 Hustler, the bomb load of the B-52, and the terrain-hugging capability of the F-111. Eventually, it replaced the former two. Unfortunately, development of the B-1 was plagued by technical issues and delays. First ordered in 1970, the aircraft did not fully fly until 1974, and by 1975, the estimated cost per aircraft had soared from $40 million to nearly $70 million. So costly was the program that in his 1976 presidential campaign, Jimmy Carter made reviewing and canceling the B-1 a key part of the Democratic Party platform. Even worse, in 1976, Soviet fighter pilot Viktor Belenko defected to the West by flying his supersonic MiG-25 Foxbat jet from his base in Chukoyevka, eastern Russia, to Hokkaido, Japan. During interrogation, Belenko revealed that the newest generation of Soviet jets, notably the MiG-31 Foxhound, were equipped with so-called look-down, shoot-down radar, which was impervious to terrain masking and could detect even low-flying aircraft. Almost overnight, the mission that the B-1 was designed for became infeasible, and when Jimmy Carter took office in 1977, he ordered the project cancelled. But unlike the early 1970s, the Air Force would not be left without a feasible strategic strike platform for long, for two replacements were waiting eagerly in the wings. One was the long-range AGM-86 cruise missile, a nuclear-capable standoff missile designed to be launched from the ever-adaptable B-52. The other was an exotic new bomber design from our old friends at Northrop, which took a radically different approach to penetrating Soviet airspace. Instead of flying low, high, or fast, it simply made itself all but invisible to radar. Enter the B-2 Spirit. The history and science of stealth technology is long and complex, and has already been covered in a previous video. For our purposes today, the immediate origins of the B-2 go back to 1974, when the Defense Advanced Research Projects Agency, or DARPA, requested information from US manufacturers on technology for reducing an aircraft's radar cross-section. This request led to the creation of two stealth technology research programs codenamed Have Blue and Tacit Blue. The former contract was awarded to Lockheed, who had previously pioneered stealth technologies like radar-deflecting geometries and radar-absorbing composite materials on its A-12 and SR-71 high-speed reconnaissance aircraft. The Have Blue project eventually produced the F-117 Nighthawk, which entered US Air Force service in 1983 and famously performed precision strikes deep behind enemy lines during the 1991 Gulf War, 1990s Yugoslav Wars, and the 2003 invasion of Iraq. Perhaps the most distinctive feature of the Nighthawk is its faceted surface, made up of dozens of flat panels, which were specifically designed using custom computer software to deflect the majority of radar waves away from their source. Screens over the engine intakes prevent the turbine blades from returning loud radar echoes, while special paint containing nanoscopic iron balls helps absorb and dissipate incoming radar waves. Meanwhile, Tacit Blue was awarded to Northrop, who took a somewhat different approach to achieving stealth. As early as the 1940s, it was known that flying wings, with their smooth, rounded contours and lack of large flat control surfaces, had a uniquely low radar cross-section. But for many years, the precise contours needed to achieve this stealth effect were beyond the ability of contemporary computers, let alone human designers, to calculate. By the early 1980s, however, technology had caught up to theory, and in 1982, Northrop created an unusual experimental aircraft called the YF-117D to demonstrate its stealth design principles. Nicknamed the Whale or the Alien School Bus, the YF-117D not only featured smoothly curved, radar-dissipating surfaces, but also a flush, paired-in air intake to reduce the radar cross-section of its engines. More importantly, however, it introduced a key technology that made both flying wings and stealth aircraft a practical reality: a stability augmentation or fly-by-wire system. As previously mentioned, pure flying wings are inherently unstable, making them difficult, exhausting, and potentially dangerous for a pilot to keep under control. This is doubly true for aircraft like the F-117 Nighthawk and the YF-117D, which, thanks to their unique stealth geometries, have the aerodynamic stability of a brick and would be all but impossible for a pilot to fly using conventional direct controls. Instead, fly-by-wire systems use computers to interpret the pilot's control inputs and translate them into the thousands of split-second control adjustments needed to keep such unstable aircraft flying straight and level. Indeed, designers joke that given a powerful enough engine and a sophisticated enough fly-by-wire system, even a John Deere tractor could be made to fly stably. Thanks to this revolutionary technology, Jack Northrop's dream of a practical, ultra-efficient flying wing could finally become a reality. At the same time, another of the fundamental flaws with the flying wing design had also been solved by recent advances in technology. As previously mentioned, fitting all the required components of an aircraft like engines and landing gear into a flying wing requires the use of an extremely thick wing section, which produces excessive drag and severely degrades the aircraft's performance. However, in the 1960s, NASA developed the supercritical airfoil, which delays the formation of drag-producing shock waves along the upper surfaces of a wing and allows higher subsonic speeds to be reached by thicker, high-lift airfoils. Today, supercritical airfoils are a key feature of most commercial airliners, allowing for efficient and fast intercontinental travel. And for more on this pivotal but rarely celebrated technological achievement and the brilliant men behind it, once again check out our previous video, The Most Impressive Hat-Trick in Aerospace History. With these design principles proven, Northrop moved on to the design of the Advanced Technology Bomber, or ATB, which would eventually become the B-2. The ATB program had its origins in the 1979 US presidential election when Republican candidate Ronald Reagan used incumbent Jimmy Carter's decision to cancel the Rockwell B-1 Lancer as evidence of Carter being soft on national defense. In response, the Carter administration announced it was building a fleet of stealth bombers far more advanced than anything that had come before and which would give the United States a definitive advantage over the Soviets. The development contract for that project, codenamed Aurora, was awarded to two companies, Northrop and Lockheed, with the former proposal being designated Senior Ice and the latter Senior Peg. Both companies opted for a flying wing design, with Northrop's proposal using smooth curves and Lockheed's reflective facets, like on the F-117. In October 1981, Northrop's proposal was selected for production under the designation B-2 Spirit, with the initial order comprising 165 aircraft. For Jack Northrop, it was the culmination of a lifelong dream, and shortly before his death in February 1981, he was granted permission to visit the Northrop factory and see the cutting-edge flying wing taking shape. Officially designated a black project, development of the B-2 was shrouded in secrecy. To build the aircraft, Northrop converted an abandoned Ford Motor Company plant in Pico Rivera, California, using a series of phony front companies for construction and parts procurement to avoid attracting suspicion. Components were always delivered by unmarked trucks under the cover of darkness. Military personnel were forbidden from wearing uniforms while visiting the factory, and employees were subjected to extensive background checks and forced to undergo regular polygraph tests to ensure their reliability. Nonetheless, in 1984, Northrop employee Thomas Cavanaugh was arrested for attempting to sell classified information to the Soviet Union, and he was sentenced to life in prison. And in 2005, Northrop engineer Noshir Gawadia was arrested, convicted, and sentenced to 32 years in prison for selling information on the B-2's propulsion system to China. Already highly expensive due to its cutting-edge nature, in the mid-1980s, the B-2 project suffered a further price hike when the Air Force decided to change the aircraft's mission from high-level strategic bomber to low-level interdictor. This change added $1 billion to the program's cost and delayed the B-2's completion by a full 2 years. To help fill the gap, in October 1981, the administration of newly elected President Ronald Reagan decided to resurrect the Rockwell B-1 program. The aircraft was modified to suit the new low-level interdictor role by reducing its top speed from Mach 2 to Mach 1.25 and significantly improving its low-altitude performance and navigation systems. The new B-1B first entered service in 1986, with the last of 100 airframes being delivered in 1988. That same year, on November the 22nd, the first Northrop B-2 stealth bomber was finally unveiled to the public for the first time, being rolled out of its hangar at Air Force Plant 42 in Palmdale, California. Access to the aircraft was highly restricted, with visitors being forbidden from viewing the rear of the aircraft. However, editors of Aviation Week magazine discovered that the Air Force had not enforced a no-fly zone over the Palmdale hangar and hired an aircraft to take aerial photos of the entire aircraft. Whoops-a-daisy. Though directly descended from the earlier XB-35 and YB-49 flying wings, the B-2 is unlike any military aircraft that came before, combining dozens of cutting-edge technologies into one elegant package. With a wingspan of 52 meters, the B-2 is a true flying wing, lacking any separate stabilizers and featuring a cockpit section and engine pods smoothly fed into the wing structure. Unlike previous strategic bombers, the B-2 has a crew of only two, a commander and a pilot, though a third can be carried as backup for particularly long missions. This is made possible by the high degree of automation present in the aircraft's control systems, which feature sophisticated fly-by-wire capability to compensate for the airframe's inherent instability. Indeed, it is possible for a single crew member to operate the entire aircraft for hours on end while the other sleeps, uses the washroom, or prepares a hot meal in the onboard galley. Powered by four General Electric F-118 GE100 turbofan engines, generating a total of 308 kilonewtons of thrust, the aircraft has a top speed of 1,010 km per hour, or Mach 0.95, a ceiling of 15,000 meters, and a maximum unrefueled range of 11,000 kilometers, though this can be extended almost indefinitely through in-flight refueling. Sophisticated terrain-following radar, GPS, and astro-inertial navigation systems allow the aircraft to fly at extremely low altitudes, hugging the ground in order to avoid enemy air defenses. Upon reaching its target, the B-2 can deliver 18,000 kilograms of conventional or nuclear ordnance, including Mark 82 and Mark 84 Dunne or iron bombs, the GPS-guided Joint Direct Attack Munition or JDAM, B-61 and B-83 thermonuclear gravity bombs, and the AGM-129 ACM air-launched standoff cruise missile. These weapons are delivered with pinpoint accuracy with the help of a sophisticated APQ-181 synthetic aperture radar that scans the terrain below and designates the target. However, the B-2's most impressive and unusual design features are geared towards a single purpose: achieving near invisibility to enemy radar. The The aircraft's main stealth feature is its unique shape, which was specially designed by pioneering computational fluid dynamics, or CFD modeling, to deflect as much incoming radar radiation away from the airframe as possible. This was a far more remarkable task than it might appear, for the requirements of stealth and aerodynamics are often at odds with one another. For example, stealth dictates an infinitely sharp leading wing edge, while aerodynamics demand something a bit thicker and more curved. Northrop thus compromised by designing a leading edge whose radius continuously changes, eliminating large constant radius sections that can concentrate radar reflections. This edge is curved downwards to better meet the incoming airstream, giving the B-2 a distinctive hawk-nose profile. The B-2 also lacks any vertical stabilizers or other large flat surfaces that could easily reflect radar, with directional control being achieved via a combination of split-brake rudders, elevons, and differential engine thrust. The engines are buried in the wing structure, while the S-shaped intakes are fed into the upper wing surface and lined with radar-absorbing material to prevent radar waves from bouncing off the spinning turbine blades. Aside from a few key components made of titanium, much of the aircraft structure is built of carbon graphic composite material that is not only light and strong, but absorbs and dissipates a large proportion of incoming radar energy. This material presented an enormous challenge for Northrop's designers. Composite materials are typically laid up from dozens of smaller layers, meaning that small errors in shape quickly compound into larger ones. As the B-2's very specific shape was instrumental to its stealth capability, this was unacceptable. Furthermore, even small gaps between the body panels could produce large radar echoes, especially at shallow reflection angles, meaning every panel had to fit perfectly. Consequently, the panels were molded from the outside in, and the internal structure designed around the panels rather than the other way around, a first in aviation history. In addition, the wing leading edges are filled with a radar-absorbing structure, or RAS, made of various compositions of glass fiber honeycomb. The aircraft skin is covered in a special radar-absorbing coating, and the windscreens feature a fine embedded metal mesh, much like the mesh on the door of a microwave oven, to prevent radar waves from bouncing around the interior of the cockpit. To further reduce reflections as well as improve aerodynamics, weapons are stored in two internal bomb bays, which feature special rotary launchers to allow ordnance to be quickly deployed while minimizing the total time the extremely reflective bomb bays are open. The devotion to achieving minimal radar cross-section applies to even the smallest details. For example, the aircraft's Rosemount air data system uses special flush-mounted air pressure sensors instead of traditional pitot tubes, as the latter would be far too visible to radar. Unfortunately, as we shall later see, this design feature would later factor into the single most expensive crash in aviation history. Although these features reduce the radar cross-section of the 478 square meter B-2 to barely 0.1 square meters, around 1 square foot, indeed, as of this recording, there is not a single recorded instance of a B-2 being targeted or fired upon by enemy air defenses. However, radar is not the only means of detecting an aircraft, and the B-2 sports a variety of features to reduce its visual and thermal signature. For example, the aircraft is coated in non-reflective paint, dark grey below and lighter grey above, to reduce its visibility in daylight or twilight conditions. Early versions injected a special chemical into the engine exhaust to reduce the formation of visible contrails, but later this was changed to a sensor that alerts the crew to the presence of contrails and a need to change their altitude. This system also automatically adjusts the exhaust temperature to directly reduce contrail formation. In addition to minimizing their radar cross-section, burying the engines in the wing also serves to reduce their thermal signature, making the aircraft less visible to infrared detectors. In addition, a special system mixes the engine's exhaust with cooler air collected just ahead of the intakes and deflects it across a large titanium alloy heatsink, cooling it and making the exhaust plume less visible. Indeed, this is the reason the B-2's engines are not fitted with afterburners and why the aircraft does not fly supersonically. Not only would afterburners greatly increase its thermal signature, but supersonic flight would generate a continuous and very loud sonic boom, as well as friction skin heating, further increasing the aircraft's thermal signature. Unfortunately, all of this cutting-edge technology and performance comes with a steep price tag. When it first entered service in 1997, the B-2's unit construction cost was estimated at $737 million. That's nearly $1.4 billion in today's money. Add to this development costs, and that figure rises to an eye-watering $2.3 billion per aircraft, making the B-2 the most expensive military aircraft ever built. And that's just the cost of building the aircraft. The B-2 is also obscenely expensive to maintain and fly. The aircraft's advanced radar-absorbing coating is very easily damaged and must be continuously maintained to preserve the B-2's stealth capability. Consequently, the aircraft must be stored in special portable climate-controlled hangars that cost $5 billion each. Furthermore, every 7 years, the B-2 receives a $60 million overhaul in which the radar-absorbing coating is blasted off using crystallized wheat starch so the composite skin underneath can be inspected for even the smallest dents and scratches. This translates to every hour of active flight time requiring 119 hours of maintenance and costing nearly $135,000, nearly double that of the B-52 and B-1, and equivalent to $3.4 million per month per aircraft. As you can imagine, US Congress was less than impressed by these staggering numbers, and the initial procurement order of 132 aircraft was soon reduced to 75. Then, in 1991, the Soviet Union collapsed, suddenly calling into question the very need for such an advanced and expensive strategic bomber. The US military was split on the merits of the aircraft, with proponents arguing for its strategic utility as a conventional bomber and critics painting it as an expensive and marginally useful waste of limited defense funds. In 1992, the administration of President George H.W. Bush approved the continuation of the program, but limited total procurement to just 20 aircraft. Then in 1996, President Bill Clinton approved the conversion of the prototype aircraft to fully operational status, increasing the total fleet to 21. The B-2 made its first public flight on July 17, 1989, flying from the Palmdale factory to Edwards Air Force Base for flight testing. The first operational aircraft started being delivered in December 1993, with the type officially entering service with the US Air Force in January 1997. With the exception of Spirit of America and Spirit of Kitty Hawk, a reference to Orville and Wilbur Wright's historic first heavy-than-air flight on December 17, 1903, all 21 B-2s were named after US states. All B-2s are currently operated by the US Air Force's 509th Bomb Wing stationed at Whiteman Air Force Base in Missouri. Appropriately, this unit is directly descended from the 509th Composite Group formed in 1944 to drop the first atomic bombs on Japan. The 21 operational aircraft are flown by an elite corps of only 80 pilots, specially trained to handle the sophisticated stealth flying wing. While most B-2 missions are flown directly from Whiteman, the aircraft have also been deployed from various overseas bases, including Anderson Air Force Base in Guam, Naval Support Facility Diego Garcia in the Indian Ocean, and RAF Fairford in England. The aircraft made its combat debut in 1999 as part of Operation Allied Force during the 1999 Kosovo War, where it was credited with dropping 11% of all NATO bombs and destroying 1/3 of all Serbian targets. B-2s deployed during this conflict flew directly from Whiteman Air Force Base to the Balkans and back, with mission durations averaging 30 hours. But while the precision strike capabilities of the B-2 and the Lockheed F-117 Nighthawk greatly reduced the collateral damage associated with earlier air bombing tactics, they also demonstrated that such strikes are only as good as the intelligence which informs them. On May 7, 1999, JADMs dropped from a B-2 struck the Chinese embassy in Belgrade, Serbia, wrongly identified as a weapons depot by the CIA, killing 3 journalists and sparking a major diplomatic incident. A few years later, B-2s participated in Operation Enduring Freedom against targets in Afghanistan and as part of the 2003 American invasion of Iraq, flying 49 missions from Whiteman Air Force Base Diego Garcia and an undisclosed forward operating base in the Middle East, and dropping more than 680,000 kilograms of ordnance. In 2001, Spirit of America performed the longest bombing mission on record, flying directly from Whiteman Air Force Base to Afghanistan in 44 hours. Even more impressively, it then landed at a nearby airbase for a quick 45-minute servicing and crew change with its engines still running, before taking off again and making the 30-hour flight back to Missouri. In March 2011, B-2s dropped 40 bombs on Gardabia airfield in Libya as part of Operation Odyssey Dawn, the NATO enforcement of the Libyan no-fly zone, while in January 2017 the aircraft dropped precision-guided munitions on an ISIS training camp near Sirte, Libya, killing 85 militants. The latter operation led to widespread criticism in the media of the waste of using a $2 billion aircraft to kill poorly armed insurgents without anti-aircraft weapons. Despite this exceptional service record, the B-2 has not been without its problems. During early flight testing, the aircraft's sophisticated radar-absorbing coating was found to be easily damaged by rain, while the terrain following radar had difficulty distinguishing rain from ground obstacles. This effectively precluded the B-2 from operating in inclement weather, which for an aircraft that's supposed to be able to deploy anywhere on Earth within 24 hours is a little bit of a problem. Thankfully, however, by the time the aircraft entered service in 1997, most of these issues have been worked out. Throughout its nearly 30-year service life, the B-2 has been continuously upgraded with all manner of sophisticated technology, including GPS navigation, satellite communications, and radar-aided targeting systems, or RATS, as well as new weapons like the Joint Air-to-Surface Standoff Missile, or JASSM-ER, and Long-Range Standoff Weapon, or LRSW, the latter of which will finally give the B-2 long-range nuclear standoff capability. Yet in spite of these upgrades, the B-2's greatest flaw remains its small numbers and exorbitant costs, which make the loss of even a single aircraft a huge financial blow. The first, and thus far only loss of a B-2 occurred on February 23, 2008, when Spirit of Kansas stalled and crashed during takeoff from Andersen Air Force Base in Guam. The two crew members, Major Ryan Link and Captain Justin Grieve, managed to eject safely, but the aircraft was completely destroyed in what is still history's single most expensive plane crash. The cause of the crash was eventually determined to be moisture in the aircraft's flush-mounted air pressure systems, which led to a faulty airspeed indication and the pilots pulling up too early. In 2010 and 2021, two other B-2s suffered serious landing accidents, while in 2022, one was forced to make an emergency landing following an in-flight malfunction. These incidents led to the entire fleet being grounded for months and cost the US taxpayer hundreds of millions of dollars in repairs. And the cost of operating the stealth bomber is likely to rise even higher as spare parts become harder and harder to come by. Indeed, due to the small size of the B-2 force, few vendors have found it cost-effective to maintain production of certain key components, forcing Air Force maintenance crews to cannibalize other airframes to keep the fleet flying. Furthermore, the B-2's stealth capabilities are no longer cutting edge, with the Lockheed Martin F-22 Raptor and F-35 Lightning II stealth fighter and strike aircraft having less than 1/10 the stealth bomber's radar cross-section. For these and other reasons, while the Air Force originally planned to keep the B-2 in service until 2058, in 2011 it was decided to retire it and the B-1 by 2040 in favor of the more advanced and hopefully more cost-effective Northrop Grumman B-21 Raider, the next evolution of the stealth flying wing concept expected to enter service in 2027. But if we've learned anything from the history of military procurement, it's that such timelines rarely go to plan, meaning that if the B-21 is delayed, the US Air Force may once again find itself with only one operational strategic bomber, the B-52 Stratofortress. Yep, the B-52, which first flew in 1954 and ended production in 1962. It has doggedly outlasted even hyper-advanced bomber designs that have come to replace it, becoming the longest-serving aircraft in US history and only the second longest-serving in the world after the Ukrainian Antonov AN-2 Colt. And for more on that particular aircraft, please do check out our previous video, the Russian military buildup of 1940s biplanes that has Ukrainian commanders nervous. Indeed, thanks to a series of modern upgrades, the venerable Buff, its crew's affectionate nickname standing for Big Ugly Fat F***, is expected to remain in service until the 2050s, making it the first military aircraft in history to serve for a century. Just goes to show that you can't beat the classics. But whatever its flaws, the B-2 Spirit remains a triumph of aerospace engineering, seamlessly integrating scores of advanced technologies into one elegant package and coming closer than any aircraft yet built to capturing the pure, distilled spirit of aviation. May she retire as gracefully as she looks and flies.